So I joined Uber ATG. By the way, Uber ATG is the subdivision of Uber that works on autonomous vehicles. I joined Uber ATG about 2.5 years ago. And what I observed was the following picture. So we have our cars driving around, gathering lots of data, terabytes, petabytes of data, right? And we have a bunch of data scientists that really want to build models. But how do they start? Okay, so you know what we need to do to build a machine learning system. You go, you need to collect your data, and you need to build some sort of a training set, test set, evaluation set. But how the data looks like for autonomous vehicle domain, right? For those who are not familiar, basically we have vehicles, they drive around, as I mentioned. The robotic system, the autonomous vehicle is a robot. So usually robotic systems are built as a set of asynchronous agents that talk to each other by message passing. And these messages are frequently recorded into logs. And then you want to use these logs to train your models. But if you look here, we have different sensors. Each of them produce different format of data at different frequencies. For example, cameras might shoot at 30 frames per second. Then we have other sensors like radars that might work at much higher frequency. LiDAR has its own frequency, right? One sweep is about 1/10 of a second. How do you take all this together and create a record that you can use for training? So the answer is not too complicated, but the thing is, oh, sorry, I didn't mention additional data sources, right? We have some supervision labels, like there are people that are going looking at the camera images, at the LiDAR scans and show, okay, this is a car, this is a pedestrian, and we also have another important source of information, which is maps. So once a researcher wants to build a model, he would join all these 3 sources, or maybe 2 sources, and create a table for itself. And the tools that are out there, for example, for TensorFlow, if you're working with TensorFlow, you're likely to use TF records. If you are a PyTorch guy, maybe it's F5, or maybe you just like working with individual files organized in directories. The thing is that each of these operations, basically data extraction, when you just come and start preparing for your job, it's not a trivial thing, especially when your system are actually huge. Because you're working again with terabytes of data, petabytes of data, and you're working with millions of records, and each record could be 10 megabyte or 20 megabytes, so it becomes tricky. It's not impossible, but the ramp-up time to learn how to do all these things, it's not trivial. And imagine you have like 10, 20, 30, 40 researchers doing all the same thing. So the obvious answer, like as an engineer, you see, okay, there is a problem here. What do we want to do? And kind of a natural answer, hey, why don't we consolidate all this? Right? Why don't we create one table for everyone to use? Because anyway, you're working with camera images. Okay, it's likely to be the same camera image for everyone. You would want to do this preprocessing or that preprocessing, but it's going to be very similar. And by consolidating all these operations of data extraction into one, you would basically enable an infrastructure engineer to specialize in this area and do it reliably, right? You don't do much mistake. You don't do that many mistakes, and you can start training right away. And we were looking basically for technology that would support this kind of repository, right? Imagine a repository with terabytes of data. Imagine a repository where each row is 10, 20 megabytes, right? How do we do that? So we looked around. By the way, and if you do that, hopefully you get a bunch of happy developers coming and seeing, like accessing the data right away, right? So we looked around what kind of technology could help us here, and so we found out that there is big data community, right? There is a well-known format, Apache Parquet. We thought, why don't we try using it, right? So we came up with a library that would allow us to stream data from Apache Parquet directly into our machine learning frameworks, TensorFlow and PyTorch, the ones that are used in our organization. And we see that we immediately get benefits of basically utilizing big data systems for data management, for creation of the data sets, for scalable procedures for data extraction, right? And again, terabytes and terabytes of data. And on the other hand, the other side of the Petastorm library is basically the utilities that we provide for researchers to access this data. In this talk today, we are going to talk about one aspect, which is basically manipulation of these huge data sets. How do we do it? How do we create the data set? How does it help us later to manage the data? And on the other hand, which tools does Petastorm provide for a researcher to access the data in the access patterns that they actually need? For example, if you have a huge data set that has both LiDAR data and camera data and radar data, mapping, labels, right? If you're working on a particular task, you might not need all the columns, right? You just want to have LiDAR data for your project, right? Can you access it efficiently, or are you going to stream tons of data that is not really used? So for this question, basically Apache Parquet is a columnar store, so it gives us these abilities. Sometimes you want to access just part of the data set, right? So you're filtering just by columns. You want a certain set of columns. For example, the frames that have pedestrians in them, right? So we have some facilities that help us filter this data row-wise as well. And there are a bunch of other features. We are going to go a little bit deeper in the following slides and see some code samples. So for dataset generation, Petastorm works as I mentioned with Apache Parquet. One tool that is used very frequently, and we are using it, is Spark. If you look at this code, this code shows conceptually how a data set is generated. For those of you who are familiar with Spark, you will be able to see right away like the familiar features. So we create a RDD with rows, and then we just store it to Parquet. Do I have a laser pointer? No. Yeah. So okay, let me show you here. If you look at the bold letters are Petastorm specific features. For example, we have a context manager there on top that helps us configure Spark and then write the additional metadata that we need for our Petastorm repository. We create Spark SQL rows, also with a function that comes from Petastorm and does the validation of the data for us. And eventually we write out the Parquet to a certain URL. And this is mostly a standard Spark code. Now, the fact that we are working with the Apache Parquet format allows us, and Spark works natively with Apache Spark format, that allows us to do queries on our data sets. So if you want to discover your data, suddenly you're starting to work with SQL. If you would be working with TF records, for example, you would need to write your custom code to go and parse the data and load it, and then you would be able, possibly with some glue code, get to manipulate the data. But here, you see on the left side, you get this SQL statement that can work directly on your data set out of the box. One of the added values of Petastorm is that allows you to store types that are not native to Parquet. And which types I'm talking about? Types like tensors that contain images or other sensor data. So Parquet, out of the box, it doesn't support anything besides scalar types and arrays. And with additional metadata, with additional schema information that Petastorm allows you to save, you would be able to read tensors directly from Parquet. And we will look in a second how this metadata definition looks like. We call it Unischema. You will see that we'll be able to specify what kind of codec do we want to use, how do we want to compress the tensors. By the way, any questions up until now? Okay. Yeah, so on the right side, you see how do we read the data. Since there are fields that are not native to Spark, like binary fields, we provide, with the Petastorm, we provide a utility to decode the data. So we get an RDD, we don't get a data frame, but this is already decoded data. So you could see the next statement, basically, let's show this image. So we have a Parquet store that you are able to store images or other tensor data, which is native to machine learning frameworks. This is something that you don't get out of the box. You don't get this out of the box with just pure Apache Parquet. So we have two main use cases. We started working about a year ago on the left use case. And the left use case is when you do store images and other tensor data. This is the principal scenario that we use Petastorm with. However, after we open sourced it, we started getting some input about other possible scenarios. For example, can we use Petastorm to read standard Parquet files that were created by other systems somewhere in our organization? Can we read them directly into TensorFlow? I don't create them, but I just go to my organizational data warehouse and I'm starting to stream data from there directly into my training procedures. So this is the scenario that we describe on the right side. But without Petastorm metadata, right now Petastorm is able to open any Parquet store and you can start reading from there directly into TensorFlow. An alternative would be, of course, you would need to write your own ETL to create your own data sets and start reading from, like having multiple stages, right? And that's about making your pipelines more lightweight, that you can go directly and hook up to the data source that you're interested in. And now we're going to show a couple of code examples. How do we access the data from TensorFlow and from PyTorch and show some features. You can see that the interface is very, very high level. You can point this function make reader. You can point it to the URL of your data set. And from there on, this is, by the way, this is pure Python example. We'll see how we hook this reader into TensorFlow in a second. But here you see the simplest way to access the data. You just point it to the URL, you create a reader, and you can iterate over reader. Reader implements the iterator. The collection interface, you can iterate through it and get your samples. In this case, you're going to get named tuples. And remember, we said there are two scenarios. One with the with tensors, basically Petastorm with complex types that are not supported by Parquet. This is the left side. On the right side, this is how you create a reader that works with just a pure Parquet file. And this would be very, very performant if you are working just with scalar data. And the left side, this is for the cases when you have stores with huge rows with tensors. And the batch reader is going to return you batches of data. If you're familiar with Apache Parquet, the data is organized in row groups. So in this case, the right side is going to read the entire row group and return it to you. Right? If you want to create a uniform sized batches, there are tools in TensorFlow that would allow you to do that. And in PyTorch, you can do it as well. But then you can regroup and get the sizes of the batch sizes that you want. And this is actually, we have a nice project that Alex is going to talk later, that he was able actually to connect it to a data store and to access it in this fashion by batches, and the performance is really good. Now, if you're working with TensorFlow, once you have the reader object, there is a small adapter function that will take this reader object, and the output is going to be a TensorFlow tensors, which means you can take these tensors and connect them directly into your graph and start your training cycles or evaluation cycles. Right? Basically, it becomes part of your graph. We also support TF Data API, which is a new way of, well, it's not that new anymore, but it's another way of accessing data in TensorFlow. It has a bunch of you can attach a bunch of downstream processing on top of this dataset, but make Petastorm dataset function on the right side turns our Petastorm reader into a dataset object that you can do the same things you do on dataset objects in TensorFlow. PyTorch, a small disclosure, most of our clients, most of our users are TensorFlow users. So we do have a PyTorch support and you can access it like this. It's not as polished as TensorFlow one. So that's the disclaimer. For those of you who are familiar with PyTorch, there is a data loader class, which is part of PyTorch. Here we have a data loader that comes from our library, and it behaves more or less the same as the standard PyTorch. So the design goal for Petastorm is to be kind of pluggable into existing tools with minimal efforts. And this is an example how our data set actually looks like, right? This is what a researcher needs to do in order to get access to the data to start developing AV models. You can see the same make reader that you saw beforehand. So we have a path to the data set. So there are a bunch of well-known paths to the data sets that we are using. You select which columns you want to read, right? And thanks to the columnar organization of Parquet, you're going to read only these particular columns, so it will be fast. And you can plot it right away. Right? But the same way would be accessing the camera data or any other data labels, etc. If you think about it, basically Petastorm allows you to create this kind of a high-level interface on top of your data sets that is very natural to the tensor-based tools, and create these big data sets that can be used by multiple projects, by multiple people. And this is basically the consolidation we were talking in the first slide. So for URLs, this is more of a kind of methodology question. How do we organize our data? So for us, we would have a bunch of well-known URLs that are for the official data sets that are well maintained. Right, Petastorm kind of works on this at the lower level. We support HDFS, we support S3, we support file URLs. Yeah, but this is basically your resource identifier, and that's it. Okay. I mentioned Unischema. So Unischema is the way, why it's Unischema? Because it's kind of schema that you can render it in different environments that we work with. We work with Spark, so we can take this definition and render it as Spark SQL schema. Or we can render it as types in TensorFlow. We can render it as types in NumPy if we are working with pure Python. And the schema is being stored together with our data, which allows us to basically take any URL of a valid data set and open it without any additional requirements. We will load the schema from there. If you think about it, Petastorm kind of feels like SQL, some RDBMS, right? You just need a connection string and then you get the data. You don't need any additional dependencies, any assumptions about the data. For example, if you're working with TF records, you need to know how to you need to decode the fields in the same way that you have encoded them. And there is, unless you do a special effort, there won't be a central place that defines how the data was encoded in TF records and decoded. Why? Because TF records is a lower level format. It doesn't know anything about tensors, shapes, and types of, at least when you do the raw decoding. Petastorm is higher level. If you think about it, you can also imagine that we could implement a backend that is based on TF records and have Petastorm on top of it, and it would still add value because of this schema, because it's a higher level schema that does not exist in TF records. And here, as I mentioned before, you can also specify how do you compress the data, or you can even provide your own custom codec if you have some special serialization mechanism, or if you know how to exploit better your statistical qualities or properties of data so you can compress them better. And of course, here also in schema, you specify the dimensions where you have variable. You can specify also variable dimensions in one of the, like in the last example over there, and you specify the type. Couple of words of what is actually reading the data for you when you are using Petastorm. Well, most of the code in Petastorm is just pure Python. We are based heavily on PyArrow, which is a very good library that that supports working within memory structure read, among others, from Apache Parquet. We have our own worker pool for decoding the data. And the worker pool, you can configure it to be either thread pool or process pool, depends what kind of data do you have. The optimal answer could be different. And these multiple workers, they work and they load different parts of your Parquet store. Each one loads a row group. It decodes the data, filters it, and writes the result to the result queue. And from result queue, we will hop into the TensorFlow world by dequeuing this element from the newly decoded element from via the PyFunc, TF PyFunc. Or if you are working with pure Python, you just get the data from the queue. There's also a shuffling queue that you can attach towards the end, and so it's mostly all of the code is Python code, except for maybe the small bridge to TensorFlow, which allows us to reuse the same code both for PyTorch implementation and for Python and for TensorFlow. One feature that was added in the last version, 0.6.0, it's part of Petastorm, but I think it's quite unique for TensorFlow community. Since we already have multiple processes as workers supported by Petastorm, we are actually able to run additional custom processing there. So you can specify when you create a reader, you can specify a certain lambda and a definition of the transform that you are doing, and your lambda will be run on these external processes. Why it's a good thing? Because there is, as far as I know, there is no good way for TensorFlow out of the box to process your data on multiple processes. The only way for you to write Python code is actually to go through TF PyFunc, and it has quite big limitations because as long as you're in your TF PyFunc, you took the GIL, the global interpreter lock, and this is going to block the entire program for you. So if you put this processing into Petastorm, even if it's not a multi-process but multi-thread implementation, it's already better because you don't acquire the global interpreter lock for the entire length of your function. For example, if you're running some NumPy code behind, or you're doing some decoding, some C++ heavy code, it's not going to block other threads, right? It's going to release the GIL during your heavy processing, right? So this is quite a neat trick. It's not directly why we created the Petastorm, but it's a nice feature we could sneak in. And this is a code example. You can see here that when we create a reader, we provide this transform spec. By the way, why is it a spec and not just a lambda? Because if we want to change the structure of the data and stream the data later into TensorFlow, TensorFlow is very strict with the types and the shapes of what you are putting into the graph. So in this case, you would need to know how the types were modified. Unischema provides enough information for whatever comes from the repository, right? But if you are changing the structure, you want to be able to describe what are you doing with the data, like how many columns did you add, what are the column names, and what are the types. Row predicates. So in order for multiple researchers to work on this one big data set of data, we said that we need ability to filter data by columns and to filter data by rows. So predicate does exactly that. You can provide a function that would be run for each row, and if it doesn't match the criteria, it's not going to be returned. But why would I even do something like this? Why don't I do this after the data is returned from Petastorm? So the answer is that in the same row, we have both sensor data, which is huge, and we have, let's say, labels. And usually I'm going to filter by labels or by some small metadata, by metadata that is small. And since I'm going to read first these small columns to see if I even have anything that matches this criteria without decoding these extra big fields with sensor data. So this is the benefit of the columnar store of our choice of underlying storage format, right? So I'm not going to read and decode the rows that we don't need, that won't match this criteria. And this is something that you cannot do, for example, with TF records, because you will need to parse the entire record if you want to to have some condition on whether you're going to use this row or not. And here, as you see, we are quite flexible. You can provide any custom function and do whatever you want. So we talked about sharding. There is an easy way to shard the data. Basically, you say how many shards you have and which one you want to read. This is implemented as basically hashing of our row group IDs and taking a modulus number of shards, right? So you'll be able to stream to your different compute nodes, different subsets or orthogonal subsets of data. Some people like to use it also for training when they train with distributed training like Horovod. So they want particular set of data to be orthogonal between different boxes. We have local caching. If you have your data set on S3 and you work locally, the data would be downloaded only once and not re-downloaded again. You see, all the features are kind of targeted towards, let's have one data set, huge data set, and we provide enough tools for the researchers to slice and dice the data they want without regenerating it, right? And hence, we simplify the whole process. Darshan will talk about this. There is less ETL reiterations. You're more confident with the data that you work with. It's easier to compare. It's easier to get reproducible results from your model. One nice feature that we implemented in Petastorm, but look what this feature is, and maybe it will hint you about our future directions. So in our case, when we're working on data from sensors and time series of this data, for example, a moving car, right? We want to train our model on a sequence of, let's say, 3 consecutive frames. How would you even do something like this, right? So you could take and store your data in one row of TensorFlow, TF record, for example. But then you would need to duplicate the data in this row to cover 3 consecutive frames. However, if we are storing the data in a sorted fashion, we can actually implement windowing on our queries, right? So we read these 5 images of the cars, let's say, and we generate 3 samples right from the memory. So instead of reading 9 images as on this side, we're just reading 5 and we are cutting them into small pieces and we return them. Why doesn't it really work great in our first iteration is because of the way the Parquet store is organized with these row groups. And basically for 2 reasons. First, if you have long sequences, but your row groups are small, you cannot cut too many windows without going into kind of a segmentation between different row groups, and this creates a problem. And second thing, like this could be a huge amount of data, right? We actually, and if you want to decorrelate your data, you would need huge shuffling queues, and this is actually not always feasible. And we are working on solutions that would work around this problem. So row group is, think about it as a block of, let's say, 50 rows, right? If you have them sorted and you need your windows, let's say you just want pairs, you'll be able to cut 49 pairs from this one row group, right? And by pair, I mean consecutive images, let's say, right? But if you want to work with larger windows, let's say I want to predict 10 seconds of into the future, I would need to have huge row groups, and actually Parquet wouldn't work that well when we, like this, let's say 10 seconds could be, I don't know, 2 gigabytes of data, and you're going to get them correlated. And this is likely not going to work well with your training procedure, right? But again, I'm starting to think about Petastorm as kind of high-level data interface that isolates the training part and like evaluation part from the data storage. So if I recognize that I have a problem like that, I would keep the interface the same, and I would think about other kinds of backends that would be more flexible for particular scenarios, right? And I would replace it without anyone knowing about it. And that's it. Now, yeah, questions?